Hello class, welcome once again to our discussion about impulse and momentum. So this video will show you the second example of our topic, impulse and momentum. So here's the example. 4 ounce baseball is pitched with a velocity of 80 feet per second. After the ball is hit by the bat, it has a velocity of 120 feet per second in the direction shown below. Okay. If the bat and ball are in contact for 0.015 seconds, determine the average impulse force exerted on the ball during the impact. Okay, so here's the solution. To apply the principle of impulse and momentum in terms of horizontal and vertical component equations. So we have here the illustration class. The ball is coming into this direction and on the left direction, and the bat going into the right opposite direction of this direction of the ball with an angle of 40 degrees at the velocity of 120 feet per second. Okay, so we can translate this into this diagram, our free body diagram. So we have here the in this direction to the left we have this mv, or the product of the mass and the velocity of the ball, then plus from the impulse and momentum equation. So the direction we have here, the impulse, no? F of x, so multiplied by the short duration of time, but in the opposite direction of the ball, and this is equivalent to this. All right. So what we're going to do now is, again, using this formula for impulse and momentum, mv, or mass times the velocity of, of this ball, then plus the impulse from 1 to 2. So assuming that from here to there, so this is r1 and then r2 is at this position, then equal to the product of mass and velocity at this point here. Okay, so solving for the x component equation, so we have, if you look at this, the ball is going on the left direction, so we assume that to be negative, and the force going to the right, so we'll assume that as positive. So considering the x component equation, so we have the negative of mv1 plus, we have f of x, the x component of the force going to the right, and due to the impact because of this bat, okay, equal to mv multiplied by, sorry, m multiplied by v sub 2, meaning the velocity, now this velocity here, and then cosine of 40 degrees. So we have here an angle here, so to solve for the x component of the force due to the due to the batting, so we have to use the cosine. Okay, and then for this part here, we have to use the conversion from the conversion of 1 pound. So we have 1 pound, 1 lb, or 1 pound is equal to 16 ounces. 16 ounces. Okay, so we use this conversion here. So because the mass here in terms of ounce, so we have to convert this into pounds because we have the unit in terms of feet, no, feet per second. So we have to combine that with pounds. All right, so here that's why we have here 4 over 16. Now because if you have this conversion, if you have 4 ounce, okay, so to convert this into pound, so 4 ounce, so converting this to pounds, so we have 4 ounce, so multiply this by, so multiply this by uh, 1 pound. 1 pound is to 16 ounce. Okay, so we have ohms at the numerator, we have ohms at the denominator, so that will be equal to 1, no? When you divide. Okay, so I'll change this color. Okay, see ohms at the numerator, we have ohms at the denominator. All right, so we have 4. This will be 4 over 16 pounds. So that's why we have here 4 over 16. So this is now in terms of pounds. All right, so we have the formula uh, M, or the mass, is equal to weight W divided by the gravitational acceleration. Okay, so this is our form here. 4 over 16, this is our weight in terms of pounds now. Then divided by G, 32.2 feet per second. Okay, so multiplied by 80. So 80, this is the velocity, all right, feet per second. Then plus F. So our delta here, it's given the problem. As you can see from the problem, it says that uh, the bat and the ball are in contact for 0.015 seconds. So this is actually our delta t, no, a very short period of time that the ball and the bat was touching each other, right? So from here, so we got f of x equal to 89 pounds, right? So we have cosine 40 here because we're just considering the x component, the horizontal component of this. Okay, so the x component, so if you have a triangle, something like this, okay, and so we have here the angle, which is 40 degrees. Okay, so this is 40 degrees. And the velocity here, which is 120. This is the hypotenuse of this triangle. Okay, this is 120. And then we want to solve this one. So this is our x component. We can have this x. So to solve for this component, you just use cosine. No? So katwa. So cosine of the angle, which is 40 degrees. Angle, which is 40 degrees. Equal to, this is equal to adjacent, which is x, over divided by the hypotenuse, which is 120. Okay, so divided by 120. So to solve for x, you just cross multiply 120, so you get x equal to 120 multiplied by cosine 40. Okay, so cosine 40 degrees. So this is the 120 cosine 40 degrees. So this is just taken from this. Now we have a right triangle here. Okay, so we got the force along the x-axis, or the x component, is equal to 89 pounds. Now considering the y component, the y component equation, we have 0 plus f sub y delta t equal to mv m v sub 2 sine 40. Okay, so now we are, if you consider the vertical part, meaning the vertical component of this, okay, so this time we have to use sine. Now we have to use sine. So sine of the same angle, 40, 40 degrees, this angle here, this angle 40 degrees, equal to, so this is our y. Okay, so opposite over hypotenuse. So our opposite is equal to y. All right, so divided by the hypotenuse, which is 120. Okay, 120 feet per second. Okay, so cross multiply, so we get y here. Y equal to 120 multiplied by sine 40 degrees. Okay, so this is the y component of the velocity, this one. So again, we have m here. Our m is, since our ball is in terms of ohms, so 4 ohms, so we use the conversion here. So we get 4 ohms, which is equal to 4 over 16 pounds. Okay, so this is equal to 4 over 16 pounds after the conversion. So we have 4 over 16. So the unit now is in terms of ohms. Sorry, pounds. All right. So this is it now. Substituting. So again, we're going to for this time the for this part here, this is 0 because you see there is no. If you look at this, there is no vertical component. All right. So because this is horizontal, this is so purely, there's no vertical component of this, so that's why we have this part is equal to 0. So the equation now is f sub y delta t equal to this. Okay, substituting the value for delta t, which is the same as the one that we use here for the x component. So we can now solve for fy. Fy is equal to 39.9 pounds. Or to get the f, the f, that is the summation of the two f here, the horizontal and the vertical components, or the x component of the equation and the y component of the equation. So we just sum up. So we have f, and this is the the horizontal is represent this I here, because this is vector, no, this is vector forces. So we have here the I component, and this is the j component, the vertical. So I here, that indicates the for the x component. Okay, and the y here, that is for the sorry, the z, the j, sorry, the j here is for the y component. So summing up, we have f equal to 97.5 pounds. So how did we get this one? So what we're going to do, because this is vector, so when you sum up vectorially, so you have to take the square, no, square and then square it, because vectorially we have f squared is equal to the summation, no? We have the fx, f of x squared plus fy squared. Okay, so that is the equation for vectorial addition. So when you solve for f, so solving for f, you just take square root. So taking square root of, so when you take square root of both sides, so it would work there. Okay, so from here, to solve for f, you just take square root on both sides. So we have f equal to the square root of f sub x squared plus f sub y squared. Okay, so that's why you have here f equal to 97.5 pounds. So that is how to get the force here, the total force, the resultant force. All right. Okay, so the problem asks us to determine the average impulse force. Okay, so this is the average impulse force. So this is what we had obtained. So this is the average impulse force, right? Okay, so that's all for this problem class. I hope you understand the explanation of this solution. Okay, thank you very much, and I hope you've understood it, and see you again in future video related to this impulse and momentum. Okay, bye for now.